What appears to be a clean energy narrative on the surface actually reveals something far more structural. This is not primarily a story about sustainability commitments or carbon accounting. Big tech is not adapting to the electric grid, it is strategically bypassing it. The largest technology companies in the world are responding to a physical constraint: the inability of legacy grid infrastructure to deliver power at the speed, scale, and certainty required by modern AI workloads. What we are witnessing is not incremental optimization, but a re-architecture of how energy is sourced, controlled, and deployed. This presentation explains the logic behind that shift, not as policy, not as ideology, but as infrastructure economics. For decades, electricity was assumed to be abundant, centralized, and reliably available through public grid infrastructure. That assumption shaped everything, from industrial planning to capital allocation. That assumption no longer holds. AI data centers are now scaling at velocities that exceed the grid's physical ability to respond. Transmission upgrades, substation expansions, and interconnection approvals move on multi-year timelines. Compute deployment cycles move in months. This creates a fundamental infrastructure mismatch, demand that accelerates exponentially colliding with supply systems designed for linear growth. Once that mismatch appears, the response is not negotiation, it is circumvention. The surface narrative is familiar. Big tech buys renewable energy credits. It signs power purchase agreements. It talks about net zero targets. That narrative is not false, but it is incomplete. The reality is operational necessity. The real drivers are infrastructure control, deployment velocity, and energy certainty. These companies are not optimizing optics. They are optimizing survival under competitive pressure, where power availability directly constrains AI capability, revenue growth, and market position. When compute becomes the bottleneck of global competition, electricity becomes a strategic input, not a commodity. The real bottleneck is not carbon emissions, it is time to power. Grid interconnection queues routinely stretch 3 to 7 years for large projects. Meanwhile, AI data centers move from planning to operation in 6 to 18 months. These timelines are structurally incompatible. No amount of policy alignment can compress physics, permitting, and construction simultaneously. When faced with incompatible timelines, rational actors do not wait. They design around the constraint. That is exactly what big tech is doing. Instead of waiting in interconnection queues, hyperscalers are co-locating solar generation and utility-scale battery storage directly adjacent to their compute campuses. This is not backup power. This is not symbolic decarbonization. This is primary energy infrastructure designed explicitly to bypass grid bottlenecks. By building power where compute lives, companies reduce dependency on transmission availability, utility upgrade schedules, and regulatory sequencing. Electricity becomes something they provision, not something they request. AI workloads do not draw electricity smoothly. They spike during training runs. They ramp during inference scaling. They stress local distribution systems beyond design parameters. The grid was never engineered for this kind of volatility at data center scale. Behind-the-meter battery systems absorb that computational turbulence, converting erratic demand into stable delivery. Storage is not about energy quantity alone. It is about temporal control. The ability to shape power flows to match computational reality. Solar generation provides daytime capacity and reduces operating costs during peak computational hours. Battery storage handles volatility and short-duration firm power. But neither technology solves long-duration continuous baseload power for 24/7 operations at scale. That gap matters, and big tech understands it clearly, which is why solar and storage are not the end of the story. They are the opening move. We are now witnessing technology companies directly underwriting generation assets that utilities historically financed and built. This includes multi-billion-dollar commitments to advanced nuclear technologies, including small modular reactors and next-generation designs intended to improve deployment flexibility. This shift is not driven by environmental ideology, it is driven by operational control and supply certainty. When compute reliability defines competitive advantage, firm power becomes strategic infrastructure. Meta has executed power purchase agreements tied to advanced nuclear development, including partnerships with TerraPower. The contracted capacity spans multiple gigawatts over the coming decade. But the signal matters more than the megawatts. Meta is functioning as an anchor customer for generation assets themselves, helping de-risk projects that would otherwise struggle to reach financial close. Demand-side financing is emerging, and power markets are quietly changing as a result. At the opposite end of the infrastructure spectrum, we observe a radically different response to the same constraint. xAI has deployed container-scale natural gas generators directly at its Memphis data center. These are modular, self-provisioned power assets optimized for deployment speed rather than aesthetic elegance or regulatory perfection. Different technology pathway, identical strategic logic. When velocity matters more than optimization, modular power becomes inevitable. Solar plus storage, nuclear contracts, modular generation. Three radically different technology pathways, one unified objective, energy autonomy. Each approach reduces dependence on grid constraints, interconnection risk, and regulatory delay. The technology choices vary, but the underlying incentive structure is identical. Control power, control compute, control outcomes. In this emerging architecture, the grid does not disappear. It becomes a constrained legacy layer, used when convenient, bypassed when mission-critical reliability demands it. This mirrors what happened in telecommunications after private fiber deployments reshaped network economics. Public infrastructure remained, but it was no longer the primary growth engine. Energy is now following the same path. A parallel power stack is emerging. On-site generation to reduce transmission dependency. Behind-the-meter storage to smooth load volatility. Direct power contracts for long-duration baseload supply. Modular capacity where deployment velocity dominates optimization. This is private infrastructure ownership, not reliance on public utility supply systems. Utilities are engineered and regulated to optimize for broad population reliability, serving millions of customers with predictable demand profiles. AI data centers behave differently. They function as concentrated industrial shock loads with extreme power density and volatile computational demand. This mismatch is structural, not managerial. It reflects architectural limits of grid planning frameworks built for a different era. Conventional energy analysis still treats electricity as a fungible commodity priced per kilowatt hour. But for AI operators, the scarce resource is not price. It is certainty, deployment velocity, and operational control. These cannot be purchased in wholesale markets or hedged through financial instruments. They require infrastructure ownership. That distinction changes everything. Private energy infrastructure is scaling faster than regulated utility capital cycles. Interconnection queues, permitting timelines, and transmission upgrades create structural bottlenecks that private systems bypass. When private power scales faster than public systems, market rules change, quietly but irreversibly. This transformation is driven by infrastructure economics, not policy mandates. What happens to power market structure, grid reliability frameworks, and regulatory oversight when private energy infrastructure grows faster than the public systems designed to balance it? This is no longer a theoretical question. It is happening now, at scale, with multi-billion-dollar capital already deployed. This video explains why big tech is systematically bypassing traditional grid infrastructure and building parallel private energy systems. Acting on these dynamics requires deeper operational understanding of power market microstructure, infrastructure economics, regulatory design, and capital deployment strategy. TaBIS publishes institutional-grade research for operators, investors, and institutions who need to move before these dynamics become obvious.